Starting in 2016, off the coast of Augusta, Western Australia, a fleet of industrial barges began a controversial operation. Over a period of several years, heavy cranes systematically lowered more than 10,000 reinforced concrete blocks into the pristine waters of Flinders Bay. Each unit weighs exactly 900 kilograms, designed to sink 20 meters down to the ocean floor. To a casual observer, this looks like an environmental violation, dumping industrial construction materials into a protected marine zone. However, this is actually the infrastructure for one of the most commercially successful aquaculture projects in the Southern Hemisphere, operated by Rare Foods Australia. They have effectively constructed a 20-kilometer-long artificial reef on what was once a barren, sandy desert. The target of this engineering effort is the Greenlip Abalone, a marine mollusk that trades as a luxury commodity. On the Asian markets, high-grade wild abalone can command prices exceeding $100 per kilogram. This facility is now harvesting nearly 100 tons of this product annually, capturing approximately 20% of the global market for this specific ranched variety. The engineering logic behind this project was driven by a failure in traditional farming. For decades, the industry tried to farm abalone on land using tanks. That method is an energy nightmare, requiring massive pumps to circulate seawater against gravity 24 hours a day to maintain oxygen levels. The electricity costs alone destroy the profit margins. The engineers at Flinders Bay realized that the Southern Ocean already moves millions of liters of water for free via strong tidal currents. The only missing element was the substrate, a hard surface for the abalone to attach to. By dropping concrete into the sand, they solved the missing variable. They are not fighting the ocean. They are leveraging its kinetic energy to run a farm that requires zero electricity to filter its water. The question remains, how does a static block of concrete replicate a complex biological habitat? Let's dive deep into the execution and the operating mechanism. The fundamental unit of this underwater infrastructure is a proprietary module known as the Abitat. These structures are manufactured using a specialized marine-grade concrete mix, reinforced with steel to withstand the corrosive saltwater environment for a minimum of 50 years. The chemical composition of the concrete is critical. The engineers utilized a pH-neutral mixture that mimics the surface chemistry of natural granite, allowing marine organisms to colonize the surface almost immediately upon contact. Each individual unit weighs exactly 900 kilograms. This specific mass is a calculated engineering compromise. The block must be heavy enough to remain stationary against the high-velocity swells of the Southern Ocean, yet light enough to sit on the sandy seabed without sinking into the sediment. To construct this reef, the company executed a massive logistical operation within their leased zones in Flinders Bay. Over several deployment campaigns, industrial barges equipped with GPS-guided cranes lowered more than 10,000 of these units onto the seafloor. They did not place them randomly. The team arranged the blocks in specific grid clusters to maximize water interaction. This capital-intensive phase required an initial investment exceeding $10 million Australian dollars, effectively front-loading the cost of the farm to minimize future operating expenses. The functional design of the Abitat relies on precise fluid dynamics rather than mechanical parts. The structure features a series of angled louvers and internal channels designed to manipulate the ocean current. When the fast-moving tidal water hits the angled face of the concrete, it creates a zone of localized turbulence and reduced velocity behind the block. This deceleration is the key to the feeding mechanism. As the water slows down, suspended drift algae and nutrient-rich organic matter drop out of the current and settle onto the concrete shelves. This process provides a constant supply of food to the abalone without human intervention. Simultaneously, the internal geometry creates a Venturi effect. The shape narrows the path of the water flowing through the housing areas, increasing its velocity to scour away waste products and sediment. This ensures the habitat remains sanitary solely through the kinetic energy of the ocean. With the concrete infrastructure in place, the project transitions from civil engineering to biological management. The organism selected for this system is the Greenlip Abalone, scientifically known as Haliotis levigata. This species is indigenous to the Southern Ocean and is prized specifically for its white meat and texture. However, the process does not begin on the seabed. It starts in a controlled onshore hatchery where environmental variables can be strictly regulated to ensure high survival rates during the most vulnerable stage of life. The production cycle begins with spawning and the rearing of larvae in land-based tanks. The aquaculture team grows these juveniles for approximately 18 months until they reach a shell length of 40 millimeters. This specific size threshold is critical. If the abalone are deployed when they are smaller than 40 millimeters, they are highly susceptible to predation by crabs and fish. If they are grown larger on land, they lose their ability to adapt to the harsh currents of the open ocean. At 40 millimeters, they are biologically robust enough to survive the transition but young enough to adapt their physiology to the wild environment. The deployment phase, often referred to as seeding, is a labor-intensive operation that cannot be automated. Commercial divers descend to the reef grids carrying the juvenile abalone in mesh bags. Unlike traditional farming where stock is dumped into a pen, here the divers must manually place the abalone onto the concrete habitats. They gently attach the foot of the mollusk to the concrete surface, ensuring an immediate vacuum seal. This manual placement is necessary to guarantee that the animal anchors itself in the correct orientation to feed on the drift algae accumulating in the hydrodynamic zones established by the block design. Once attached, the biology of the abalone undergoes a radical transformation driven by the physics of the environment. This is the defining difference between ocean ranching and tank farming. In a land-based tank, the water is relatively static. The abalone does not need to exert significant energy to hold onto the surface, which leads to a physiological composition that is higher in water content and softer in texture. In contrast, the abalone on the Flinders Bay reef are subjected to the constant high-energy swell of the Southern Ocean. To survive, the animal must constantly engage its adductor muscle, the large foot that constitutes the edible portion of the meat, to maintain its grip on the concrete. This continuous isometric exertion functions effectively as a 3-year physical training program. The result is a significant increase in muscle density and a reduction in water content. This physical stress creates a meat texture that is firm and distinct, replicating the exact quality profile of wild-caught stock, which commands the highest premium in the marketplace. For the next 36 months, the system operates with zero human input. This period represents the primary economic advantage of the ranching model. In a traditional farm, this 3-year growth phase would require daily feeding, constant water filtration, and continuous electricity consumption. On the concrete reef, the abalone graze on the algae captured by the hydrodynamic design of the blocks. The nutrient exchange is entirely passive. The ocean current delivers the food, and the abalone cleans the concrete surface as it grazes, preventing biofouling from clogging the water channels. The operator effectively removes the operating expenses associated with feed and energy from the balance sheet for the entire duration of the growth cycle. The monitoring during this phase is minimal, consisting primarily of periodic security patrols to prevent poaching and biological sampling to track growth rates. The data shows that the abalone grow at a rate of approximately 30 millimeters per year, fueled by the nutrient-rich cold water upwelling from the deep ocean. The cycle concludes when the abalone reach a shell length of 140 millimeters, which is the optimal market size for export. The harvest operation mirrors the deployment in its reliance on skilled labor. Commercial divers return to the seabed using surface-supplied air systems to allow for extended bottom times. Harvesting is a physically demanding task because the abalone clamp down on the concrete with immense force when disturbed. Divers use specialized prying tools to detach the abalone without cracking the shell or damaging the meat. The catch is immediately placed into crates and hoisted to the support vessel, where it is placed in an ice slurry to drop the core temperature instantly. This rapid cooling preserves the glycogen levels in the muscles, ensuring the meat remains sweet and tender. From the seabed to the processing facility, the focus is on maintaining the quality that took 3 years of hydraulic pressure and biological adaptation to create. The result is a product that is technically farmed but biologically indistinguishable from a wild catch. From a financial perspective, the deployment of the concrete reef has proven to be a highly effective capitalization of the seabed. The project has moved beyond its experimental phase and now delivers a consistent annual harvest of roughly 90 to 100 tons of abalone. To put this volume into perspective, Rare Foods Australia now supplies approximately 20% of the world's total production of ranched Greenlip Abalone. In their 2023 financial reports, this operation generated revenues exceeding $4 million Australian dollars, proving that the model is not just ecologically sound, but commercially viable. The core economic strength of this model lies in the radical reduction of operational expenditures. In a land-based aquaculture facility, the cost of electricity to run pumps and chillers, combined with the cost of manufactured feed and antibiotics, constitutes the majority of the operating budget. On the Flinders Bay Reef, these specific input costs are reduced to zero. The ocean provides the energy for water circulation, the ecosystem provides the algae for feed, and the natural spacing of the blocks prevents the disease outbreaks that necessitate medication in crowded tanks. While the input costs are minimized, the output value is maximized through product positioning. Because the abalone are subjected to the physical stress of the ocean currents and consume a natural diet, the meat develops a texture and flavor profile identical to wild stock. While standard tank-farmed abalone typically trades between $30 to $40 per kilogram, the ocean-grown product commands prices upwards of $80 to $100 per kilogram. This premium is also driven by the nutritional density of the meat. A single 100-gram serving of this Greenlip abalone provides nearly 20 grams of high-grade protein with less than 1 gram of fat. Furthermore, due to the mineral-rich diet of ocean algae, the meat is naturally fortified with selenium, omega-3 fatty acids, and iodine. It is effectively a bioavailable superfood, which drives its high demand in the health-conscious luxury markets of Asia. The primary export destinations reflect this valuation. The majority of the harvest is shipped immediately to premium markets in China, Japan, and Hong Kong, where it is a cultural staple for high-end banquets. In Europe, the product is distributed to Michelin-starred establishments that demand specific textural consistencies for sashimi. Furthermore, the company has implemented a strategy to maximize the utility of their seabed lease by introducing a secondary product line, Ocean Cellared Wine. The engineers realized that the environmental conditions at the bottom of the reef, constant cool temperatures, total darkness, and high pressure, are theoretically perfect for aging wine. Leveraging the existing diving logistics, they now deploy cages filled with bottles of wine onto the reef alongside the abalone. The hydrostatic pressure at a depth of 20 meters exerts a consistent force on the corks, increasing the seal density, while the gentle motion of the ocean accelerates the aging process of the tannins. These bottles, encrusted with barnacles and marine growth, are retrieved after 12 months. While the original bottle might retail for $30, the ocean cellared version sells for anywhere between $150 to $500 per unit. This secondary revenue stream transforms the seabed from a simple farm into a multi-purpose storage facility, extracting maximum value from every square meter of the leased ocean floor without requiring any additional land or energy infrastructure. However, operating a farm without fences in one of the roughest oceans on Earth introduces a unique set of uncontrolled variables. The primary operational risk is security. Because the inventory sits unguarded on the seabed, it is highly vulnerable to poaching. With a market value exceeding $100 per kilogram, these reefs are lucrative targets for illegal divers. To mitigate this, the company has to maintain surface surveillance and coordinate with local marine authorities, effectively treating the patch of ocean like a high-security vault. The second major threat is geophysical. The Southern Ocean generates some of the most powerful swell energy on the planet. While the 900-kilogram mass of the Abitats is calculated to withstand normal conditions, extreme storm events can still generate enough force to displace the blocks or, more dangerously, cause the sandy seabed to liquefy. If the sand shifts significantly, the concrete structures can be buried, suffocating the stock. The engineering team must constantly monitor seabed topography to ensure the foundation of the farm remains stable. Despite these risks, the environmental data presents a compelling counter-argument to the critics of artificial structures. Contrary to the initial fear that dumping concrete would degrade the marine environment, the Abitats have functioned as a catalyst for biodiversity. The structures have transformed a barren, monoculture sandy bottom into a complex reef ecosystem. Biological surveys indicate that the concrete does not just support abalone. It has attracted rock lobsters, schooling fish like duffish and snapper, and various sponge species that had previously vanished from the area. By providing hard structure and flow complexity, the project has inadvertently restored a thriving food web. This proves that industrial intervention, when designed with hydrodynamic intelligence, can actually enhance rather than deplete the natural environment. Looking at the macro picture, this technology is now being evaluated for international export. The model is not limited to Western Australia. It is applicable to any coastline with strong, cold currents and flat, unproductive seabeds. Feasibility studies are already underway to adapt this system for the waters of New Zealand and other regions in the Southern Hemisphere. It represents a scalable solution to the global protein deficit, moving away from resource-heavy land farming toward passive ocean ranching. This brings us to the final question of resource management. We often view concrete as the enemy of nature, yet here it is the foundation of a restored ecosystem. Do you believe we should leave the barren ocean floor in its natural state? Or do we have a duty to intervene with engineering to regenerate food sources? And for the seafood enthusiasts watching, have you ever tasted abalone produced from this specific reef? Leave a simple yes or no in the comments below. Thank you for watching.
Yeah, I reckon we'll celebrate tonight.